try to create a fault in one of the transmission line, and then we will see how our rotor angle changes using the swing equation. Okay, so let us look at this equivalent model of single machine internet bus system. Let me learn about this single machine internet bus system. Silent. We did not learn about single machine internet bus system. Anyway, I assume you learned it. So you have this single machine internet bus. When you find the equivalent circuit of this single machine internet bus system, you get this kind of equivalent circuit. Then after that, you have this equation where E dash is the generator's machine's internal voltage with and this is how we find the maximum power supplied by the machine, where PE is the electrical power, which is equal to E dash, where E dash is the generator internal voltage, EB is bus voltage divided by total reactance of that single machine infinite bus system, sine of delta, where delta is the rotor angle, okay, generator rotor angle, which is equal to Pmax. Pmax is value here. Why I'm presenting this is because this relationship is very important for us when we simulate this transient stability. Okay, so next thing you need to know is this equation of motion or swing equation. Okay, so where H is the inertia constant in megawatt second by MVA. Okay, and this omega naught is the initial speed of rotor. Delta is the rotor angle. We have PM, mechanical power, Pmax, we have electrical power maximum, and sine delta. You keep this in mind. Are we? Okay. These are not very important. This is also not very important. Of course, for theoretical understanding, important. Now, when you see this equation, swing equation, this swing equation is a non-linear differential equation. Okay, non-linear differential equation. So to calculate, to find the solution for non-linear differential equation, you have some numerical approach, such as Euler's method of finding. I do not know whether you have learned it or not in your theory. Oh, let me record this first. Okay. Okay. Anyway. Okay. So these numerical integration method you have, such as Euler's method of finding a solution for for ordinary differential equation, which is non-linear. Okay, you also have modified Euler's method to find the solution. You also have Runge-Kutta method. Okay, you have many methods, but you will later see how these methods are implemented in our simulation later. Okay, so our interest is, we take a case. One is the example 13.1 is the question which we will do practical on. Okay, in this example, we will examine the transient stability of a thermal generating station consisting of 4 555 MVA, 24 kilovolt, 60 Hertz units supplying power to an infinite bus through 2 transmission line. You can see here 2 transmission line. Okay. system is the same as, no, this, you just forget this, but we need to look at this single machine infinite bus system, where four machine is connected to infinite bus by a transformer having reactance J0.15 and two transmission line here with upper transmission line with reactance J0.5 and lower with J0.93. And we will create a fault, ground fault in this line. Then we shall see how angle changes. Okay. Okay. So now you are given with mechanical power. This is mechanical power. The generator is operating at overexcited excitation. You have generator terminal voltage here. You have bus voltage here. Okay. Then this is transient reactance. Transient reactance in d-axis, which is 0.3. You have inertia, which is 3.5 MW as MVA. You have zero damping coefficient. Okay, so we need to find power at different conditions. That means pre-fault. What is the electrical power that is flowing through this from single machine to? We need to find what is the electrical power flowing through this transmission line before fault, during the fault, and after the fault. Okay, so here they have calculated that before fault, the electrical power flowing through that transmission line from a single machine model is 1.351 sine delta. Okay, before fault. During the fault, it is 0. Okay, because everything is shorted during the fault. During the fault, the power is 0. Okay, then after the fault, the power flowing through that transmission line from single machine model is 1.1024 sine delta. Okay, now this they have used numerical integration method to find a solution. They have used RKM method. Now this is very important. Before the fault, maximum electrical power, you can note it down. Maximum electrical power flowing through that single machine to infinite bus is 1.351. During the fault is 0. After the fault is 1.1024. Okay. Now you need to know these initial values. The initial value of rotor angle is 41.77 degree, and change in rotor speed is 0 per unit. Okay, you need to know this, and you also need to know what you have to know from this to simulate this this fault is, you need to know h value of h, which is equal to 3.5 MW as MVA, and you need to also know initial speed of the rotor. The initial speed of the rotor is given here. It is 377 rad per second. Here, 377 rad per second. So omega naught is equal to 377 rad per second. Agree? Then you also need to know power at different instance of our simulation. That means before fault, what is the maximum power? Maximum electrical power that is flowing through the transmission line is 1.351. That is before fault. Then 0 during fault, and 1.1024 after fault. Away. Okay, and you also need to know initial conditions, because when you solve differential equation, you need initial condition to get the exact solution of the differential equation. Okay, you must have studied in your mathematics class where when you solve differential equation, you require initial conditions. Yes, when delta at 0, what is the value of delta at time 0? What is the value of rotor speed at time 0? What is the value of rotor angle at time 0? Okay, so delta naught, that is another delta naught similarly. So delta naught is the initial value of rotor angle, which is equal to 41.77 degree. When you convert this into radiant, you multiply 41.77 multiplied by pi, and you divide it by 180, and you will get 41.77 multiplied by pi divided by 180 will come around 0.729 rad. Okay, so this is, and you have also change in rotor speed, which is equal to 0 du. So these are the informations that we require to model our to plot this graph. We want to replicate this graph. We want to see the critical clearing angle, okay, for various clearing time. Wait, okay. Then, but to model this, let's look back to our swing equation. Let's look at the swing equation, and then we will solve this swing equation in Simulink. Do you have experience on modeling or using Simulink in MATLAB? Anyone of you have idea on using Simulink? Anyone of you have idea on using Simulink or experience before? This question is very, very important. Okay, 2h by omega naught e square delta dt square is equal to maximum E max times delta. Okay. So what you will do here is you will take this 2h by omega naught to right hand side, and it will become d square delta dt square is equal to omega naught 2h Tm e max times delta. Yes.
You're not so audible, sir. We can hardly hear you, sir.
I'm not audible. Am I audible now?
Yes, sir.
Okay. So from where did you miss?
From
anyway, okay. Anyway, you need to know single machine infinite bus system, where a machine is connected to infinite bus via a transmission line. The transmission line can be 2 lines, 3 lines, 4 lines, but here in our case we are considering 2 transmission lines, in which one of the transmission line is experiencing a ground fault. Away. So when it experiences a ground fault, we need to look at different situations whereby what is the electrical power flowing from our machine to infinite bus before fault, during the fault, and after the fault. There are three cases, 3 situations. Okay, so to model that, we need to know about the swing equation. So this swing equation, in this swing equation, we will solve this swing equation to find how our rotor angle changes for various clearing time. Okay. Now, the information we require to solve this Swing equation is value of h omega naught. The omega naught is initial rotor speed. 2 is just a constant. Pm is mechanical power. P max is the electrical maximum power. Okay, so this electrical maximum power is different for different situations. Before fault, after fault, during the fault, the value of this P max will be different. Okay, so you need to note this down, and you also need to note the initial rotor angle, initial rotor rate of initial change in speed. Okay, need to know that. So our focus is on this question, example 13.1 here, where all the information is given. The information given here, PM is 0.9. Okay, PM here is 0.9. That means mechanical power is 0.9 of PU. 0.9 PU. Then you also have H. See H 3.5. You also have omega naught. From here you can see omega naught, which is 377. Anna, 377 rad. So when you take this swing equation, the constant 2h 2h to the right hand side, 2h by omega naught to the right hand side, it becomes omega naught by 2h. If you write, you will understand. Take 1 minute to revisit what I have explained. 1 minute. If you have doubt, you can ask me. If you do not understand or you do not get any information, then simulating is very, it will be challenging work. So take 1 minute to understand. I will wait till 56. You can open the PDF that I have uploaded and see. Okay, your time is up now. Now, from this question, what information we got is we got the value of h 3.5. We got value of initial rotor speed, that is 377 rad per second. We got the information on mechanical power, PM, which is equal to 0.9. We got information on maximum power for different situation. Pre-fault maximum power is 1.351, and during the fault 0, and post-fault 1.104. Okay, we also got the value of initial rotor angle, that is 41.77 degree. And when we convert that into radian, that is equal to 0.729. And we also got the value for change in rotor speed, that is equal to 0 per unit. Okay, so these are the information we got. So now we will proceed on to simulating this fault condition. Okay. Now we will open the MATLAB. What will you do is you can note this down. You can note this down. What you can do is you have to you can note the steps to perform the practical later. I know you won't be able to perform with me, but you can see how I am doing and then note the steps and then you can do it yourself. Okay? Good. Now, to do the practical, what you need to do first is step number 1, create a folder on desktop named.
Sir, we can see screen, sir.
No, I have just stopped the screen. Just listen to me, listen to my explanation. Step number 1, create folder named Power System Operation and Control Laboratory on your desktop. Okay? Okay, let me share the screen. How to do that? First, share the screen. Are you able to see it?
Okay. Yes, sir.
Now create a folder. Step number 1 is create a folder on desktop named Power System PN Power System PS Power System Operation and Control Labs on your desktop. Okay, so this is your folder on your desktop. Okay, now open that folder and create another folder named put one underscore transient stability, stability. Okay, then open this transient stability, and what you can do next is copy this file directory here. From here you will get the file directory. Okay, copy that folder directory. That means this is the address to this folder. Copy that and open MATLAB, and then you can paste on this directory. Okay, directory tab. That means when you paste here, you are going your MATLAB working folder is the folder that you have created earlier. Power System Operation Lab folder. Then inside it you have transient stability. Okay, here. So this is the working folder for our MATLAB. So whatever work you do and whatever data you save will be saved in that folder under Power System Operation Lab folder. Within inside it there is another folder, transient stability. Inside that folder everything will be saved. Okay. Do you have experience on working with Simulink? Is there anyone who has experience on working with Simulink? No one. So I should assume there is no one who has experience. Okay. Okay, so I will start from the basic. Your step number one is completed. Step number one is to create a folder on the desktop. Then inside that, you name a folder with power system operation lab, and inside it you have, what do you have? You have transient stability. Okay. Then you copy the directory of that folder on MATLAB directory tab here. Okay. Then press enter, and you will go to that folder. Okay. Now, next is to open a Simulink. After opening MATLAB, you need to open Simulink. You have two ways with which you can open Simulink. First one is you can type Simulink in the command window, SIMULINK, like this, and press enter. Then you will be able to open Simulink. Second option is you can tap on this Simulink icon. Then you will be able to open Simulink. Either way, you can open Simulink. Okay, two ways. So let me do with this typing of Simulink text on window and then tapping on enter. I'm tapping on enter. So when you tap enter, then Simulink will open. But you need to be very patient. You don't press this icon more than once. Just press once and then wait for your system to work. Okay, if your system is very, very fast, then it will open instantly. Otherwise, you have to wait, like my system. My system is slow, so it takes some time to open it. How, Omega, do you have any doubt? Do you have any doubt?
No, sir.
Okay.
Clear, sir.
Okay, good. Okay. So this practical you won't find online. Okay. So you listen carefully. Let my system work. Minute. You want me to record the session?
Yes, sir.
Recording the session. Wait. Let me see how to record this. While my, okay. You want me to record all of this, or just the practical?
Just the practical is fine, sir.
Just the practical is okay, sir.
Okay, then I will start recording from now. Okay.
Okay, sir.
Okay. So this another report with another report. That's it, man. I'm trying to record. But no, the record anything. I don't know how to record. Give me a second. Record be to be me now. But wait, I will use other this. I'll record this session, but you can view this at the same time. Okay. It's me. I'm working on recording our session. This is my window capture. Okay. Recording. Okay. Okay, I'm recording now. Window capture. Okay, are you able to hear me?
Yes, sir.
Recording the I could have worked on it. I forgot. Okay. Capture. Okay. Now you're able to hear it, no? Good. I'm recording this session. Okay. Okay. Now, let's go to our practical. Are you able to see? Are you able to see the screen?
Yes, sir. Yes, sir.
Okay. Now the Simulink has opened.
Sir.
Then what you will do is you will create a new folder here. You will tap onto this create model, and then you will create a new folder. Now, when you look at Simulink, when you look at our simulation, when you look at the swing equation, we require, what do we require? We require integrator block, because when we integrate this right hand side of our equation, swing equation, then we will get the value of first we will get the value of speed, then we will get rotor angle. Imiga second order differential equation domain. So when we integrate 2 times this second order differential equation, we will get the solution for the integrated variable. Okay. Okay. Now open 10 minutes. Hi. And you open Nansam Studio. Can I record and then share the link so that you all can download and learn yourself.
Yes, sir.
Yes, sir.
Otherwise, you will take ages.
Sir.
Anna Nansam Studio my system. So what I will do is I will record my this lab. I will upload it in YouTube. Then I will share the link. Okay.
Yes, sir. Okay, sir.
Then this is the end of our today's practical work. Next we will do load frequency and load frequency control. Okay.
Okay, sir.
Yeah.
Sir.
Oh.
Any report maintain begoya, sir.
Bego में report maintain bego तो होते. हाँ.
Gachira chango bina, sir.
I sample chike जाऊँ तो गाना. I will upload one sample for lab report.
Okay, sir.
In VLE, you have to write similar to that report.
Okay, sir.
Okay. Yeah.
Okay.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.